DC applied to an RLC series circuit. Now let us consider an RLC series circuit let V be the RMS value of the applied voltage, I be the RMS value of the circuit current, then voltage drop across the resistance would be VR, voltage drop across the inductor would be, let it be VL, and voltage drop across the capacitor be VC. So your VR will be equal to I into R, where your voltage VR and I are in same phase. Your VL is I into XL, where XL is the inductive reactance, and your current lags the applied voltage, that is this VL, by a phase angle of pi by 2. VC I into XC, where your current leads the voltage VC by 90 degree. Now, if we club up all these three phasor diagrams, then in case of pure resistance, let us see VR and I are in same phase, inductor VL leads or current lags by phase angle of 90 degree, and VC current leads by an angle of 90 degree. Now let this be the resultant voltage V. And this is VL minus VC. If you take VC on this OY axis in phasor position, it would becomes minus VC. And phi will be the angle. Whether your current would lag or lead, that would depend upon VL minus VC. Now here, what is V? V would becomes VR square plus VL minus under the root, or I R square XL minus XC का whole square, और V by I is R square XL minus XC square, and that is the impedance of the circuit. And unit of impedance ohm. This may be represented in terms of vector quantity or complex quantity, that is z may be written as r plus j xl minus x. Moreover, now whether your circuit is to be considered inductive or capacitive, or your current would lag the applied voltage V or lead the applied voltage V, that will depends on your VL and VC. In case VL is greater than VC, then this VL will dominate, or XL greater than XC, your circuit would be inductive. What would be your power? Power would be, XL would be greater than XC. Then if applied voltage is Vm sin of omega t, then what would be the current? Im sin of omega t minus phi. And accordingly we will find the power, and power would be Vi cos phi. Vi cos of phi. Now, and we can plot the wave curve, power curve accordingly, as we have done in case of RL series circuit. You just go through RL series circuit, thereafter you can draw the wave curve, power curve in accordance to your RL series circuit. Now, if your VL is lesser than VC or XL is lesser than XC, means XC dominates. That means you have the value on the OY dash axis, or the operator would be multiplied with minus J. Means J cube means minus J. It means then if your applied voltage is Vm sin of omega t, your current would be sin of omega t plus phi. And if you solve it for power, as in case of RC series circuit, your power would be Vi cos of phi. Now, third case, when VL would be equal to VC or XL is equal to XC. What will be the impedance of the circuit? Impedance of the circuit would becomes equal to because your XL minus XC would be equal to 0. Hence the impedance of the circuit would becomes equal to R, and your circuit will behave like a pure resistive circuit. And your power would be in that case, if the applied voltage is Vm sin of omega t, I would be Im sin of omega t. So means in that particular case, your current and voltage would be in same phase, and your power would be V into I. Or whether we have understood all these three cases, or we can broadly write that our current in case of RLC circuit, if applied voltage V is Vm sin of omega t, then current would be Im sine of omega t minus plus phi. That would depends whether your current lags or leads. If your sign is minus, means your current is lagging the applied voltage by phase angle of phi. If it leads, it will be plus omega t plus phi. If both XL would be XC, then this angle would becomes 0. And in all the cases, power is given by VI cos pi. So, in single phase circuit, active power consumed in the circuit is given by VI cos of phi. If your phi is minus, means current is lagging, so it means current is if the value is phi, if the XL is greater than XC means lagging, XC is greater than XL means leading, and it is equal to 0, this phi would be 0 when XL would be equal to XC. But all the cases we will have this phi power will be VI cos of phi. This phi can be find out. Tangent of phi in case of RLC circuit. Yes, that is XL minus XC by perpendicular divided by base, or tangent of phi may be written as so your RLC circuit results gives result for all the cases whether circuit is pure resistive, this XL minus XC is 0. When the circuit would be pure inductive, phi will be 90, power would be consumed would be 0. Pure capacitive, phi 90, power consumed would be 0. In case of pure resistive, phi is 0, both voltage and current are in same phase, the power would be VI. So means this is the generalized equation for single phase AC circuit. Power is VI, where V is the RMS value of the applied voltage, I is the RMS value of the current, phi is the phase angle between this voltage and current. Resonance in RLC series circuit. The circuit said to be in resonance when reactance of the circuit is 0 or XL minus XC is 0 or XL would be equal to XC or Z will be equal to R. When XL would be equal to XC, the reactive component of the circuit would be 0, hence your impedance, that is R square plus XL minus XC square, the Z would be equal to R. So that can be, circuit can be in resonance by varying, because your inductance is fixed, capacitance is fixed, but your XL is given by 2 pi Fn, XC is given by 2 pi Fc. So by if we vary the frequency, at certain frequency both could be equal. Hence the frequency at which resonance occurs, or your inductive reactance would becomes equal to the capacitive reactance, is known as resonant frequency. Frequency at resonance. Let it be given by F naught. Or so this we know, at resonance XL minus XC would be 0, or XL would be equal to XC, or 2 pi F naught L 1 by 2 pi C, or F would be equal to F naught square would be equal to 4 pi square L C, or F naught 2 pi under root L C. So in series resonance, or in series circuit at resonance, at this particular frequency the circuit would be resonance. And at this particular resonance, when your impedance would becomes equal to resistance, hence your current in the circuit would be given by V by R. Or this current, this is the I naught is the current at resonance. And this will be the maximum value of the current. So we can represent the conditions of resonance graphically, different parameters graphically. At resonance, let us note it. With respect to frequency, because the frequency is the variable. By varying the frequency, we can put up the circuit in the resonance. At resonance. Let this be frequency, this be the other parameters. Your resistance remains same irrespective of the frequency. Your XL is inductive reactance is given by 2 pi FL. C is fixed, F is variable, so your XL would be with the variation of the frequency. XL is directly proportional to F. Let this be the noting of your XL. XC 1 by 2 pi FC. or Xc is inversely proportional to the frequency. Xc lies in the fourth quadrant, means it occurs after a rotation of 270 degree, means the operator is multiplied with j square, jq, becomes to jq, that is equal to minus of j, that is your Oy dash xh, and it is inversely proportional, represent it minus x. Now, at a particular point f naught, where both XL would be equal to XC, resonance would occurs. Let this be the point. This is the F naught resonance frequency where XL would be equal to XC. If we plot the curve for XL minus XC, that will be in between. XL minus XC. Now, with the variation in the frequency, your reactance varies, and at resonant frequency it becomes 0. And with the variation of the reactance, your impedance varies, and your impedance would be minimum at R. And your impedance would be minimum means your current would be maximum. That means your impedance may vary. If you plot for the impedance, that is Z impedance, and your current would be maximum and this will be I. Right, resonance, your current would be maximum. So this we can represent our graph for different parameters, for resistance, reactance, impedance, and for current. This is for current, and current would be maximum at I naught is 0. Initially current would be 0, because your inductor would behaves like a open circuit, and thereafter rises to maximum value, and when Xc starts greater, your power factor would be leading, hence it will start decaying. Now, at certain currents, let the current would be I naught by root 3, 2. We have 2 points. These are half power frequency point, because at these particular points your frequency becomes half, because power is given by I naught square R. At resonance power is I naught square R, and at this current power would be I naught by root 2 ka square R, or I naught square R by 2. So power becomes half in comparison to power at resonance. So these points are known as half power frequency point, and these points may be denoted by F1 and F2. Frequency at which your power becomes half, and the band of this frequency is known as bandwidth. The bandwidth is F2 minus F1. Bandwidth, either sides of these points or these frequency would be on the both sides of the resonant frequency, and the band of these frequency would known as band. Quality factor at resonance. Quality factor can be described by different ways. This first one, it may be described in terms of voltage magnification. And that is the voltage across the inductor at resonance to the voltage applied, or voltage across inductor, sorry, capacitor to the voltage applied. That is, ratio of quality factor may be defined as ratio of voltage across the inductor to the applied voltage, or voltage across the capacitor to the applied voltage at resonance. Or quality factor can be found out VL naught, V naught, and this will be the XL naught by R, because that applied voltage would be equal to I naught into R, or that would be two pi F naught L R, or that will be 2 pi 1 by 2 pi root LC into L by R, or that will be equal to 1 by R root LC. So quality factor at resonance is given by this. Also, voltage across the apex. Yes, voltage across the capacitor by V naught, that is XC naught by R, and that is 1 by 2 pi F naught C R, or that would be root 2 pi root LC 2 pi CR, and that will be equal to 1 by R root LC. So quality factor is ratio voltage across the capacitor to the applied voltage, or voltage across the reactance to the resistance at resonance. Quality factor may also described in terms of energy stored to the energy dissipated. Quality factor is the ratio maximum energy stored to energy dissipated per cycle at resonance, and your maximum energy stored is given by half Li naught square, and energy dissipated is I square R T naught, that is the time period of the cycle. Or this will be can be written as 1 by 2 pi 1 by 2 L, because the maximum value of the current is root 2 of RMS value. Divided by I square R time period F naught. So this one is cancelled. You have to cancel. You will have 2 pi L by R F naught 1 by 2 pi root L C. So you will have quality factor 1 by R root L C. Quality factor we also described as the higher selectivity for the tuning coil, and ratio resonant frequency to the bandwidth or